of polymers. So a quick overview of what this presentation will contain is we'll look at what FDM is just briefly and generally, and then we'll look at how it works. And then we'll look at some different parameters that affect the final product, its properties and quality. And then finally, we'll look at some materials that are used and why they're used. So first of all, FDM is when an object is built by selectively depositing melted material in a predetermined path layer by layer. And it's the most common technique industrially, and it's one of the most common techniques domestically as well because it makes up the majority of desktop printers. This is often the first technique that people learn how to do when they first get into 3D printing. And it's one of the most cost-effective as well, with printers ranging from roughly around $200 from a lower end desktop printer all the way up to $100,000 or more for high quality industrial FDM printers. So now we can look at how it all works. So it starts out on a design software where the object is modeled and then saved as an STL file. And then it is sent to a pre-processing software, which then slices it into thin layers. From then, it is downloaded and sent to the FDM machine itself. And then from here, it starts by feeding the filament from room temperature all the way up to the extrusion head. And as you can see, there is sometimes a support filament and a part filament, but a lot of times it's just a part filament that is being extruded and used for the support structure as well. So once it reaches the extrusion head, it is then, the filament is melted into a semi-liquid state and then extruded from the nozzle onto a heated build platform or bed. And the extrusion head itself moves typically in the X and Y direction, where the build platform moves in the Z direction. So now we have a general idea of what this looks like. We can go into detail on the extrusion head, which is where most of the process is controlled and takes place. So as mentioned before, this room temperature filament will get fed up to the extrusion head. And then from here, it reaches the rollers or the pinch wheels, which then grab onto and create small indents into the filament, which then force it down to the liquefier. And then this force must be great enough to counteract the viscous forces that are needed to heat the polymer and to reduce its cross-sectional area as it then comes out of the nozzle in that reduced diameter. So once the filament has reached this liquefier portion, heat is applied to it so that it reaches past its glass transition temperature, which then allows the polymer chains to loosen and slip and align, resulting in a semi-liquid phase of the polymer that's able to be flow out of the diameter of the nozzle and then extruded onto this heated build platform. And so this build platform is often heated as well in order to allow adherence to the layers and to the support material and can counteract effects such as warping. So now that we have seen how it works, we can move into some different parameters that control the end quality and the final characteristics and mechanical properties of an FDM printed object. So the ones we'll look at are the layer thickness, the orientation, the print and extrusion velocities, and then the temperature of the nozzle and the temperature of the build platform. So each of these parameters, when set individually, do not have a great effect on the final product. However, when they are set according to each other, then it has a greater influence on its final properties and its quality. So first of all, we can look at layer thickness. So layer thickness affects the heat dissipation and the build time. So an increased layer thickness means the number of layers will be less, and this will lead to an increase in the strength of the part. However, if the layers are less and they're thicker, then this means that the staircase pattern from the layers will be more prominent and thus a lowered surface resolution. On the other hand, if the layer thickness is decreased, the accuracy and the geometry of the structure is increased, but then so is the build time. Theoretically, the layer thickness can range from 0 to all the way up to the diameter of the nozzle, but the most optimal layer thickness would be 1/2 of the diameter of the nozzle. Any smaller and the build time just becomes too excessive, and then any less, and as mentioned before, that surface resolution is lowered. And then next we can look at the orientation and how that affects the final outcome of the product and the model. So orientation directly impacts the internal structure, the strength, the build time, the surface roughness, the accuracy, and the support structure. However, it's impossible to satisfy and optimize all of these features. So most often, the most critical one that is looked at is the strength of the material according to orientation. So this leads us to seeing the anisotropic behavior of FDM printed materials. And this is when in one direction, the strength is decreased compared to the others. For example, if a force is applied parallel to the layers that are being laid down, then the strength is much greater than if the force is applied perpendicularly to the layers, as in the z-axis, that strength is decreased. So it's just one area to keep in mind when building the part, and to consider where the strength can be compromised and where it needs to be taken into consideration. So next we have the print and the extrusion velocities. The print velocity is the velocity at which the extrusion head moves in the x and y direction, and then the extrusion velocity is the rate at which the material is being extruded from the nozzle. And the relationship between these two significantly can impact the final product, and the best outcome is when these two velocities are closely matched. If one is much greater or smaller than the other, it can lead to burning of the material, change in the diameter of the material, and the wire drawing effect. And this is when the material being extruded does not adhere to the layer laid down right before it. And so as the nozzle goes along, that material is extruded out and it's not adhering, so it looks like a wire coming out of the nozzle. And then another parameter to keep in mind with these two velocities is the distance of the nozzle head away from the layer being deposited. That should also be adjusted according to these two velocities as well. And then finally, we have the nozzle and bed temperature. And these two can greatly affect the properties. So a change to the nozzle temperature can lead to material getting stuck in the nozzle and then causing blockages. It has also been found that when the nozzle temperature goes below a material's glass transition temperature, it's difficult to extrude and for the layers to adhere to each other. And the change in the build platform temperature cannot allow the material to adhere to the bed. And we'll get to see a few examples of what these temperatures would be set to for specific products. And then we also have an equation that relates the print velocity, the extrusion velocity, the diameter of the filament, and the diameter of the nozzle. And this is particularly used when first setting up the printer. One of these variables may be unknown or can be adjusted through this relationship to determine what the optimal variable in the number should be. So now we can move on to look at some of these different materials that can be used and why we use them. So we're looking at polymers this week, and there are two different types of polymers that we can see. We have thermosetting and we have thermoplastic. So we're going to be looking at some of those differences and why we use thermoplastic particularly. So thermosetting polymers are the polymers that are not able to be melted again and again. An example of this would be like a shampoo bottle. If you were to heat this up, it would simply burn because it has a network polymer structure, which does not allow chains to realign when they have reached glass transition temperature. And this can be seen because these bonds here in the cross-linked and the network are covalently bonded, which are much stronger than these van der Waals bonding between these chains. And so in order to break these covalent bonds, in order for the chains to loosen and slip and align, it would have to be a temperature to break those strong covalent bonds, which would also ultimately end up breaking the backbone of the chains as well. So it wouldn't allow it to be heated up again and again. And then we have thermoplastic materials and polymers that can be melted again and again. These polymers have a linear and a branched molecular structure, which allows these chains to loosen and align and move when they're heated up, allowing it to form into that liquid state. And this is the key characteristic that's needed in fused deposition modeling because the material needs to be able to be heated up into that semi-liquid state in order to extrude it through the nozzle. And it also needs to be able to maintain those original properties, which it's able to do. So now we can look at a few examples, and one of the most common examples we can see is ABS, and this is an amorphous copolymer, which means that these three monomers are bonded together to form long branched chain made up of acrylonitrile, butadiene, and styrene. As you can see, these are these monomer structures over here, and we're going into some detail about how these contribute to ABS's properties. So acrylonitrile is a synthetic monomer, and it contributes to the chemical resistance and the heat stability of ABS. And then we have butadiene, which is the monomer in synthetic rubber, and it contributes to ABS's toughness and its impact strength. And then we have styrene, which is the monomer found in foam packing material that you may have used before, and it contributes to rigidity and processability of ABS. And all these properties make ABS widely used because of its good prototyping ability due to its high durability, its low cost, and its fine feature detail. We can also see down here, as mentioned before, the nozzle temperature and the bed temperature and the glass transition temperature, about what those would need to be set to in order for it to be printed. And then we also have PLA, or polylactic acid. And this is a polymer that can come in two different phases. We have PLLA, which is higher in mechanical strength and toughness, and then we have PLDA, which produces a semi-crystalline polymer. And then what separates these two phases, as you can see down here, is the plane on which the CH3 molecule is on. So PLA is becoming more and more popular because it is derived from renewable sources such as cornstarch and sugarcane. And it's also biodegradable, which combined with its good mechanical properties and good processability, it is the more environmentally friendly option compared to petroleum-based polymers. And it can also be used in biomedical applications. It's being used for implants, sutures, and stents. And it's becoming more and more popular over ABS as well because it requires this lower nozzle temperature and bed temperature, meaning that it requires less energy to be printed. We can see that example of 180 to 230 for that degrees Celsius for that nozzle temperature compared to ABS's 210 to 250 degrees Celsius. And then we can move on to some more materials that are compatible with FDM. So as we saw, we had PLA and ABS, and those are those high commodity, they are lower in cost, they require a lower printing temperature compared to our engineered and high performance polymers. So a few examples and what this means. An engineering polymer they're known for their good mechanical and thermal characteristics, their resistance to wear, high dimensional stability. And this is why they can often be found in aerospace and automotive industries being applied there. And one example specifically, we have PC or polycarbonate, and they are known for its toughness, its good strength, durability, flexural strength, and one of its most important is that it's transparent, which means that it can be used as a substitute for glass, especially because it is less dense, and because when it's broken, it will not have those shards like glass does, so it's a great substitute. It's also well liked because of the good surface quality it provides and the good layer bonding when 3D printing. However, it is more, as mentioned before, it is more expensive compared to PLA and ABS, and it does require that more energy to be printed as well. And then one example we can see above is it's being used as a light fixture, and then as mentioned before, it can be replaced, it can replace glass. And then next we have our high performance polymers, and these are known for their thermal resistance, their good mechanical properties and chemical resistance. And then these differ from engineering polymers when it comes to the cost of the material. It is more expensive, but it also means that they are more temperature stable and they have better mechanical properties. And then one example of this is PEEK, or polyether ether ketone, and it has a similar stiffness to bone, so it can be used for implants. One that I found especially interesting was that it can be used for cranioplasty material, which is bone repair to cranial defects, as you can see in this picture above. And it's beneficial in this area because it's lighter and it's more comfortable. And unlike metal implants, it does not conduct temperature, which protects the brain from suffering those negative effects of heat conduction. So in all, for this presentation, we learned about how FDM works, looked at some different factors and parameters that affect the final quality and the mechanical properties, and then we looked at some materials that are used in FDM and why those are used. Here's the schedule. Last week, we looked over the overview of additive manufacturing. This week, we looked at the fused deposition modeling, specifically of polymers. Next week, we'll look at the stereolithography of polymers, then we'll move on to metals and alloys and how those are being used in additive manufacturing, and then finally end with ceramics. Thank you. Any questions?